This is my presentation for Lab 3 circuits. The purpose of this lab was to demonstrate the workings of current and voltage in simple circuits involving resistors and capacitors, and we used voltmeters and multimeters to measure the values. Preview of our results: the potential difference of negative 0.94 volts for the 47 ohm resistor was recorded, and for the 100 ohm resistor it was negative 2 volts, so delta V was negative 0.02 volts for the whole circuit. The 10 ohm bulb took 10 seconds to charge and 12 seconds to discharge, while the 20 ohm bulb, the RC circuit for that, the capacitor took 18 seconds to charge and 21 seconds to discharge. Below you can see two pictures of our circuits and us collecting the data. The physics principles we used are the loop rule, Ohm's law, and the capacitance formula. For our experiment, the circuit was measured with the two multimeters. We used 47 and 100 ohm resistors, and there were two 1.5 volt batteries for net 3 volts. This is a little diagram of our circuit. The system was the circuit, the surroundings were everything else, and this is just a picture of our circuit from our lab data collection. For calculations, our I1 is equal to I2, which was 0.02 amps. Potential differences were negative 0.94 volts and negative 2 volts. And the net potential difference was negative 2.94 volts. Without resistors, it was 2.91 volts. So the total delta V is expected to be 0, and our experimentally determined one was very close to 0, negative 0.03. This is a little graph of the voltage over time. You can see after the battery it charges it up, and then the resistance brings it down to 0 back as the loop goes fully around. The current increases from 0.02 amps to 0.06 amps when you put the ammeter in parallel instead of in series, because there's less current at the resistor when you open an alternate path through the ammeter, because the ammeter has little to no resistance. For the RC circuits, we used a 1 farad capacitor. For the 10 ohm bulb, again, it took 10 seconds to charge, 12 seconds to discharge. 20 ohm bulb, 18 seconds to charge, 21 to discharge. This is a little graph of the expected values. We expected it to have decayed much faster, as seen in the graph. Similarities and differences: the observed discharge time was 12 seconds, but on the plot it was 6 seconds, because we assumed there to be no resistance in the connecting wires, which isn't really true, and no external E fields or magnetic fields that affect the circuit. So for our error, the multimeter could have been slightly inaccurate because we did get changing readings even though nothing about our circuit was technically changing. There could be inconsistencies with timing, especially because it was hard to tell when the bulb was fully out or fully on, because it's pretty subjective. So inconsistencies in timing would be a big error, and the wires have some slightly negligible but still non-zero resistance, so that would have also impacted the calculations. For the what if question, if there was no resistor, the ideal model would predict the capacitor to fully charge instantaneously, but obviously this wouldn't happen in real life because zero resistance isn't actually possible. So with zero resistance, all the charge would instantly flow in and instantly build up the potential difference on the plates, but that just can't happen because anything is inherently going to have resistance. The measured time is 6 seconds for the other situation. For the situation that we had with the wires, it was 6 seconds, so it's pretty different from the ideal situation. That's the end of my